In this tutorial, we'll explore several methods of modeling a return distribution. Recall, a financial return distribution provides a visual illustration of the frequency and magnitude of various returns. A model of a distribution assigns a probability to each measurable subset of possible returns. Often this will take the shape of a smooth curve that, loosely speaking, matches the observed return distribution. One advantage of using such models is that a probability can be assigned to potential returns that have not yet been observed. This is particularly useful when data history is limited. For example, we want to know the probability of losing 5% on any given day, and all we have are 2 years of returns that only observed a worst one-day return of -4%. To compute this probability, we would need to have a model to extrapolate this information. Other advantages include forecasting and use as a tool for comparison to the observed data. We'll begin our exploration with one of the most common and traditional models, the normal distribution. The normal distribution is sometimes referred to as the bell curve because of its symmetric bell shape. It is relatively easy to compute and does well measuring central tendency. It is characterized by two parameters, average and volatility, also known as the mean and standard deviation. The mean identifies the average or relative middle of the distribution, while volatility measures the spread or width of the distribution. Some of the limitations of normal distributions include its underestimation of extreme events or fat tails and its inability to measure asymmetry. To illustrate this first limitation, underestimating fat tail risk, let's explore in more detail how the normal distribution models risk. Recall, a distribution model assigns a probability to each measurable subset of possible returns. In the case of a normal distribution, we can compute the probability of a return being within plus or minus one standard deviation. The model defines this outcome to occur 68.2% of the time. Within 2 sigma is defined to occur 95.4% of the time, and within 3 sigma is defined to occur 99.7% of the time. In terms of days, a 3 sigma event is predicted to occur, on average, once in 741 days, based on historical S&P 500 data. In reality, this event has happened on average every 137 days. This computation can be extended. At a level of 10 sigma, an extremely unlikely outcome is predicted to occur every 500 sextillion years. However, in reality, these events have occurred on average every 15,000 days. Given these limitations, it may be natural to ask what distribution models can more accurately measure extreme events or asymmetrical return distributions. There are more distribution models than can be covered within this tutorial that address these concerns, such as log normal, stable, or mixture distributions. For example, the student t distribution has 3 parameters: location, scale, and shape, or degrees of freedom. The first 2 are similar to the normal distribution's mean and standard deviation. This third parameter, the degrees of freedom, allows for fat tail estimation. This distribution is still symmetrical, but a related distribution, the skewed t, adds a 4th parameter, which allows for asymmetrical returns. Based on data from 1998 to 2008, we can see that using a skewed t distribution provides risk estimates that more closely match reality. For example, a 5 sigma event, which is expected once over 13,000 years using a normal distribution, is predicted to occur once in 2.7 years using a non-normal skewed t model. The ability to model fat tails has provided a closer estimate, 2.7 years, to the realized observed 3.6 years on average. Further information relating to deciding which distribution model to select is covered in more detail in our next tutorial, Fitting Distributions. This completes the Modeling Distributions tutorial.